All right. Thank you everyone for coming. Today we have Professor Yinhai Wang, who is a professor in transportation engineering and the founding director of Smart Transportation Applications and a research laboratory at the University of Washington. And he's going to give a talk about AI applications in transportation engineering. So take it away whenever you're ready.
Thank you, Julia. Hello, everyone. Thanks for the opportunity to talk to you all. It's a great honor to be invited by FTC 18225 High Definitions team. I know your team did terrific and received the Inspire Award last year for Washington. So thanks a lot. So today, I would like to share my experience in AI applications in transportation engineering. Feel free to ask questions during my presentation, or you can wait until the end to ask questions. Everybody have to use transportation in your daily life. For example, you may go to school either using your parents' car, you drive your own car, or you use school bus. It's going to be very unusual if you don't see any transportation news on the newspapers. For example, here are some examples from the newspapers worldwide talking about the challenges in transportation engineering. Maybe you all heard about the supply challenge in the United States. Actually, this is not just a problem within the US. It is a global problem. You heard about a lot of vessels waiting in the LA area. For example, these ships have a lot of the containers needs to be unloaded and then shipped to places that need them. At the same time, these containers need to be loaded on the ships and brought back to the places to carry more goods to the United States. So President Biden ordered, the LA port to be working, harder to try to resolve the congestion of the cargo goods. At the same time, there's also challenges in transportation safety. This figure actually shows the number of fatalities on the roadway. You see, we have about 40,000 people killed every year on the roads. The black line is showing the trend of the fatality rate. We have been seeing a general declining trend until recently. In 2020, you see a 24% increase in the fatality rate. And the first half year of 2021, you see another 18.4%. So this is quite shocking. As you know, we have safer and safer vehicles. Newer vehicles are normally equipped with a lot of safety features. Why do we still see the challenges, like the increase in the fatality rate in 2020, in the year that we have a lot of people working from home, fewer vehicle on the road. And the first half year in 2021, why we have this continuous increase. So these questions need to be answered by not only the transportation professionals, but also everybody who use transportation for their shopping, their recreation trips, or their daily commuting. Why we see the increase in the fatality rate, why we have so many cargo ships congested at the ports. We need talents like you people and try to think about these things and find a solution. In the transportation area, we're facing a serious workforce challenges. For example, the right side is a report published by Transportation Research Board. It mentioned that in 5 to 10 years, about 50% of the current transportation agency employees are eligible for retirement. You can imagine if so many people retired, we are going to have a serious workforce challenge to handle our transportation infrastructure the regular needs of a transportation system operations. There are plenty of opportunities, and you people may want to consider, is transportation your future job? If you're thinking about these things, I would like to encourage you to consider the University of Washington. You see this beautiful picture, right? I took one day when I was walking on the campus. We have a very strong transportation engineering program in the civil and the environmental engineering department. No matter what your interest might be, as far as you're interested in studying or doing transportation job, you could consider the UW civil and environmental engineering. So you see we have these faculty members in different areas, like myself in both the computer science area and the transportation area. Like Professor Mackenzie, he studied electric vehicles, EV charging. Professor Linda Boyle, she has the industry engineering background and also a transportation professor. Like a Professor Goodchild background in mathematics, she studies like urban freight, logistics, and Professor Ed McCormick, he has a lot of experience in geography and working on intelligent transportation systems. And similarly, Professor Jeff Ban, his background is automotive engineering. He's also working very hard in the transportation network and system analysis. Professor Cynthia Chin conducts big data analytics relevant to public policy and transportation planning. We also have resources on campus, like the Pacific Northwest Transportation Consortium is a U.S. Department of Transportation funded University Transportation Center that supports transportation research, education, and workforce development. We have the grants to pay our undergraduate students to go to conferences. If they have a paper to present in transportation area, we can pay their trip so they can go to the conference, talk to professionals, and exchange ideas for research and studies. Now, coming back to the future job, our transportation graduates have a great choice. So normally you could consider working in the classical transportation area, like working for transportation agencies like a Federal Highway, Washington State Department of Transportation, or the consulting companies. Or you can go to the new mobility areas. For example, we have students working for Amazon, for Apple, Microsoft, Zillow, a variety of new companies that's doing things with transportation. So anyway, I just want to give you a quick introduction about the opportunities in transportation area. And I hope some of you may consider working in this great area with a lot of challenges. At the same time, there will be also a lot of opportunities. So coming to the challenge we're facing. So how do we address the problems we have? Normally, as you can see from this slide, transportation problems are complicated. You can see from this picture, human, bicycle, automobile, all congested together. You can also see by the road, there are people selling things. There's just a very complicated picture in global range for addressing transportation problems. You have to consider it's not simply a technical problem. It is actually associated with culture, political issues, etc. I'm glad to see actually the first tech challenge has been focusing on transportation related issues. Like this year's theme, freight frenzy, is actually moving things around, right? So this is typically a transportation problem. You move a particular item from point A to point B. How do you move this efficiently and safely? So this is exactly what we are doing in transportation area. So I hope your experience with the first tech challenge will build your foundations, to take a very successful career in the transportation area. So coming back to what we have to solve our transportation problems, over the past years, we have deployed a lot of traffic sensors, as you can see from this particular slide. Maybe while you are traveling on the road, you can see detectors like the leftmost one is the acoustic sensor. It's basically detecting traffic based on the sound. And the second from the left is the microwave radar sensor. It detects vehicles, bicycles, and the pedestrian based on the round trip travel time of the radar beam. And the middle one is the infrared sensor, and then the loop detector, video sensor, combined sensor. So these are the typical traffic detectors that collects data on our roadways. And we have accumulated a lot of such data. Recently, we also have new information sources. For example, the Internet of Things may have already the sensor in your shoes. It actually broadcasts the information that could be detected. And by matching the media access control address, we know where this person was and where the person traveled to. So the purpose is not tracking a person, it's just measuring how many people are using this particular path, what's the travel time. You all know your cell phone actually has the positioning function. If you're using, for example, Google Map, you are contributing to the Google's traffic data. At the same time, you benefit from Google's service like Google Map. Twitter, Facebook, Google Search are also providing data. For example, you were in San Francisco yesterday and you conducted an online search. And we know this particular device was in San Francisco, and maybe today you are back to Seattle. You are using the same computer to do an online search, and then we know, okay, this person come back to Seattle, and then we know the person traveled a long distance from San Francisco to Seattle. Autonomous vehicle, a lot of companies are developing autonomous vehicle systems. As you know, autonomous vehicle will be detecting surrounding objects automatically, and for the vehicle to make a decision, stop or keep driving, or making a turn or not, right? So there are a lot of data associated with automated vehicles. There are other things, for example, this garbage bin may also have a sensor reading some electronic signals that could be used for transportation. So the classical data stream combined with this neural data stream, so that forms the transportation big data. And this is actually a very important resource that the transportation professionals could use to understand a particular phenomenon of transportation and try to identify the issue and develop a solution to address it. Now we are facing a lot of data. We're certainly also facing a lot of transportation challenges. As briefly mentioned, we have a safety challenge, we have an efficiency challenge. You all know we also have a big congestion in Seattle area. How do we make a good use of the data and try to find a solution to fix our problems? So this is always a challenge, but in the recent years, with the increasing amount of data and the new problems, so we need new idea, new solutions, new algorithms, try to address these challenges. In the past 5 to 10 years, we have actually worked a lot with the increasing amount of data. But what we typically do is put the data together and conduct some data mining, data analytics, or visualize the data. What you see here on this slide is actually the DriveNet system developed by the Smart Transportation Applications the Research Lab at the University of Washington. So this is my lab. We receive 50 million lines of loop detector data each day, and we can understand, where it's congested, when the congestion start, where the congestion spots start, how it growed. So this kind of information. But this is only about congestion. So if we want to understand the transportation problems better, for example, why we see an increase of the roadway fatalities in 2020. So we need more than just visualizing the data. We need to identify how the relevant data are connected. So We don't have a parametric model that will be able to do these things. And then this makes us to consider what kind of other solutions or other methods are ready for us to use. Not sure how many of you know the Go game. The Go game started in China. Is a very old game. So basically, you see, you have the white stones and the black stones. So the two persons play against each other. So this has been something, a lot of humans are pretty good at. The Chinese player and the Japanese or Korean players. So they are very good. But things changed in 2017 when a robot, the DeepMind is a company. They've developed a software. It's called AlphaGo Master. They beat the best human player. His name is Jie Ke, and that's 3-0. The first game, I think Jie lost marginally. The second and third game, he lost miserably. There's no chance to win. So basically, that's a kind of milestone showing if artificial intelligence could be used appropriately, it can demonstrate great power and could be used for addressing some critical challenges. Another interesting I want to share with you is AlphaGo Zero is a newer version of the software developed by the same company. Just in about 40 days. So the AlphaGo Zero beat AlphaGo Master. That's the software that beat the best human player 3-0. So it's 89-11. And this AlphaGo Zero basically does not learn anything from human. AlphaGo Master still use the past, Go game records, and the robot learn from the human player's knowledge. But this AlphaGo Zero used the so-called reinforcement learning. So basically, this robot just play against itself. And by playing again and again in a very fast pace, if you play with human need to consider, think, right? That take time to play. But this particular robot could use the fast computer to play with itself very quickly and learn the knowledge. So basically, after 40 days since this AlphaGo Zero was developed, is no doubt that this particular robot is the best Go player. So no human player can even go against it. So that demonstrates the power of this particular technology, which is artificial intelligence. Maybe you're wondering, what is artificial intelligence? There are a lot of different definitions, but this definition seems to be more appropriate, so I share this with you. So it is basically the capacity given by humans to machines to memorize and learn from experience, to think and create, to speak, to judge, and make decisions. So basically, you want to develop a particular robot, try to emulate humans' thinking, human style of working, the brain working, so working style, and try to learn from the knowledges or learn from the rules, so it can conduct the jobs automatically, like a human. So there are several major kinds of artificial intelligence methods. Artificial intelligence is quite broad. It includes a lot of different approaches. Inside artificial intelligence, there's also the machine learning. So a lot of the work now people are doing, the newer works are actually machine learning. And inside machine learning, there's another subdomain called deep learning. So basically, these things are very frequently utilized. With the newer computing devices, deep learning is possible, and also with the huge amount of data support. Why do we consider AI could be potentially very useful for transportation? I can show you a few examples later, but this is from a Stanford report. This is a 100-year study on AI by the Stanford University. It said transportation is likely to be the one of the most, the first domains in which the general public will be asked to trust the reliability and the safety of an AI system for a critical task. Maybe you have heard about a lot of automated vehicle testing and the future of automated vehicle, etc. So automated vehicle rely heavily on AI, because you can understand that for a vehicle to drive automatically, you need to understand where the vehicle is, what kind of surrounding moving objects or fixed objects are. So what is the traffic rule, how the vehicle should make a decision, stop, make a turn, or continue to drive, right? So there are all these things needs a kind of artificial intelligence. Let me show you a few examples, but before we get to there, I want to emphasize that AI is generally developed for the general applications. For transportation system, if you want to use AI, you have to consider traffic infrastructure systems characteristics. For example, our roadway network has certainly the rule, right? Like traffic moves from upstream to downstream. Even you see 405 and I-5 are two most important corridors in our area, but they don't interact with each other until you see a kind of link connecting the two roadways. For example, I-90, 520, right? So these are the link roads. Without the link roads, these two roadways will not interact. But when you look at an AI model, so AI considers every node point connect to each other, right? So that's kind of complicated. If you use the transportation infrastructure systems characteristics, try to simplify the application in transportation area, you could make the computation load lower and also convert faster, right? So those are the important things to consider. If you want to know more about how this kind of characteristics can be considered, you could look at a paper I listed here. This paper was written by my students and me. So you could access the paper and read. If you have any questions, and let me know. Here's another example. So we look at how we can use AI to predict traffic speed. So the left side figure is actually what we observe. Let's say based on the traffic sensor data, here's the speed distribution. You can see the red color means the speed is lower, right? So here's the legend. Using in this particular research, we use the bidirectional long short-term memory approach. So the right figure is actually what we predicted. So you predicted, for example, you predict the next day, next week, next month. So after you make the prediction, you can wait until that day, right? When things happen, you can compare the two. So you can see actually the AI-based prediction worked really well. It actually matches the actual observation, almost identical. Yeah, so this is really a good performance. And this AI approach certainly overperformed, much better than the classical method that we tried in the past years. Another example I want to show you is actually a collaborative work between the University of Washington, the city of Bellevue, and also Microsoft at the very beginning. So we three units work together, try to use video analytics to identify the hard conflicting points at the intersection. For example, you look at this intersection, you see this area has a, like we consider this a heat map. This indicates there's a lot of interaction between vehicles and pedestrians. If there are more interactions, that normally match to more like accidents in this particular area. So this particular work started with the partnership Bellevue, Microsoft, and University of Washington, and later expanded. We have also other entities joined, like Together for Safer Roads, and some companies. So we can actually collect the data and use the AI try to identify which kind of vehicle is moving through the intersection. For example, is this a truck? Is this a car? Or this is a pedestrian or bicycle? So after you identify the user, the roadway user, you can see is there near miss. We can see like if the two vehicles conflict to each other and missed very narrowly, and that's called a near miss. Near miss could map to a traffic crash. So by looking at the trajectories, as you can see here, we know how frequent these vehicles interact to each other and in what situation. So we're looking at this 124th Avenue Northeast and NE 8th Street in Bellevue. So this is actually before we take a kind of action to change the situation. So you see the left turn in this particular intersection caused a lot of problem. And this is actually evidenced by the trajectory analysis. So after we use the video analytics, we recognize automatically vehicles, bicycle, pedestrian, and how they interact with each other. If we look at the time to collision, was this considered a near miss, or is it just a normal interaction? And then we recommended the city of Bellevue to change the traffic signal timing and also facing. So they add actual left turn signal. So after they do this, we see this kind of interaction reduced by 65%. And you can imagine 65% near miss events could certainly link to 65% reduction of the potential crashes. So this is going to be a huge benefit for our roadway users and for our city. So because of this work, we received the USDOT's like a National Roadway Safety Award. So this is actually the current Secretary of Transportation, Pete Buttigieg. He was making a speech at this event. And the lower right picture is Franz Lauenhurst. He's actually the city of Bellevue's planner. He actually lead this whole effort. He's holding the plaque of the award. So, so this is another example showing how AI could be used to our daily life in transportation. And by finding the problem and then making the adjustment, we could potentially save lives. So these two examples I just mentioned are a kind of very, very rough examples. I only gave you, in general, what we did, right? We did not give you some details. I want to present a more detailed example to show how AI could be used. And this particular example is a research project at my lab. So this is basically using AI to improve roadway safety. You see there are a lot of traffic crashes, and there's a new technology called connected vehicles. Maybe you have heard about this. Connected vehicle, the idea is every vehicle and every pedestrian could be connected by wireless communication, and the roadway infrastructure could connect it with the roadway users. Roadway users could be vehicles or pedestrians or bicyclists. And by knowing where it's dangerous, for example, in this intersection, there may be a black ice in here. And then this vehicle found it and tell the infrastructure. So the infrastructure received the message and then broadcast to vehicles coming to this area. Here, there's some danger here. You may want to pay attention. So USDOT has a website, posted message like connected vehicle has a huge potential to save lives. It could reduce delay and also reduce the number of crashes, could go up to like 80% traffic crash reduction. But how do we implement this particular idea? So connected vehicle concepts has been there for several decades, but there's no real success stories based on that. And then we have been considering how do we develop a kind of a magic device. So this device could be connecting to the traffic control center and also connecting to the roadway users like drivers, bicyclists, or pedestrians. So how this particular magic device should look like, what kind of functions it should have. So this is actually our research, problem, and our objective is to develop something that could be connecting the road users to the traffic control center. And, that's like a road user and infrastructure connection, and the connection also among the roadway users. So this particular sensor that we developed, we call this mobile unit for sensing traffic. In short, we call it MUST. And this is a sensor with the IoT functions, and also could use the V2X, means vehicle to everything application. So basically, you can consider this is the application used by connected vehicle to make the roadway users and the infrastructure to be communicating with each other. In this particular technology, we apply computer vision, media access control address sensing. So this is like if you have an electronic device that you can use for internet, you must have a media access control address. And this is more or less serving like an electronic ID. So this device could be uniquely identified. We also use edge computing. Maybe you wonder, what is edge computing? So you can consider just computing using a small device. And the small device may be deployed on site is called an edge device. You can just consider that's a device with very limited computing power. Your cell phone is an edge device. Maybe Raspberry Pi and NVIDIA, like a Jetson device, they also consider edge device. We also use the regular artificial intelligence. So everything is integrated together in this particular sensor to conduct the kind of work. So we want to use this technology, try to do the data collection and data fusion. And then with the data collected all by the same unit from the same location, we can do data analysis and then supporting the decision making. For example, should we turn on the green signal for this direction? Should we let people know they should pay attention when they pass through here? Should we close this road because it's too dangerous, etc.? So this kind of decision. The particular project that we actually got the support from Norwegian Public Road Administration. So this is actually, this picture shows Norway's E8 corridor. This E8 corridor is connecting the fisheries inside the Arctic Circle all the way to the border with Finland. So the salmon fish produced by Norway will be carried by truck, go along this corridor, go across the border with Finland, and get to the Helsinki airport to upload on the plane and then deliver the fresh salmon fish to, for example, Japan, China, the consumers there. You can imagine if this roadway is congested due to whatever reason. Maybe you also know inside the Arctic Circle, in the winter time, they have like 24-hour dark time, no daylight. But in the summer, you may also see 24-hour daylight, right? So in the winter, it could be very challenging. The temperature could go negative 40 degrees Fahrenheit. So to ensure this roadway is reliable, for the freight transportation, and that's quite important. So that's why the Norwegian Public Road Administration has been working with the University of Washington startup and try to develop the technology and deploy the technology, try to measure travel time from point to point, and then estimate the reliability. If this is beyond the reliable travel time range, we know something must have happened, and then we can inform the Public Road Administration to assign incident response truck to the location. So we plan to install 9 sensors along this road, so we can measure 8 segments of the road, the travel time reliability. But how do we conduct the job to tell this, this particular segment's travel time is reliable? We have to do a bunch of work, detecting, for example, incidents and sending the warning message to the traffic centers. We also need to look at the travel time from point to point. Let's say the segment from the beginning to the end. What's the travel time? But is the travel time in the reliable range? That depends on road surface condition, right? You can imagine if this is dry road pavement surface, vehicle can drive faster, right? If it is wet, for example, right after the rain, vehicle will be slower. If this is snow covered or ice covered, it will be even slower. So you have to estimate this based on the roadway condition. So you have to detect road surface condition. And you also need to know, is this truck or car? Truck travel normally slower, right? And sometimes it's very difficult to separate, wet pavement to like ice-covered pavement or dry pavement even. So you have to look at what is the temperature and the humidity. Is this more likely in the icy situation, right? So these are all things that we need to address in this particular research. You see this picture, the left side picture is actually the sensor we developed, and here's the Star Labs logo. And here are the functions that we can do V2X communications, road surface sensing, vehicle counting and classification, travel time estimation, temperature and humidity sensing, and also sensing visibility. A lot of these functions are implemented with the AI-empowered methods. Specifically, let's talk about exactly what kind of method we did and how we address this challenge. So this flow chart is showing, for example, you get the video stream, and the stream actually will be going through this particular dash block first. So we try to use the optical flow trajectories, try to see where the moving objects are going. So this is trying to identify where's the road surface, because you don't want the human interaction. After you install the sensor, human have to tell you, here's the road. And then due to whatever reason, you adjusted the video's field of view, you have to do that again, right? So this is automatically detecting where's the surface of the road. And then we look at the roadway background and the foreground, so we can look at where the moving blobs. And then we can use this method, try to identify, is this moving blob a truck or a car or other kind of vehicle? So another challenge we have to deal with is we're using the edge computing device, and the computing power is very limited. So we have to consider using a very simple approach, does not consume a lot of computing resources, try to be the kind of trigger. So if we found there's a vehicle showed up, and then we need to start the AI approach, try to identify what kind of vehicle this is, and we'll do that. Because every time you trigger, the AI approach is going to take about 2 to 3 seconds to compute. So you have to deal with, when you need to start that. Otherwise, the computing resources we have on the sensor will not be sufficient to cover all the computational needs. So here are some results from our research. You can see from identifying roadway surface perspective, this is when we get started, and this is when we detected some vehicles. When we detect sufficient amount of vehicles, you see the roadway surface is identified, like the lower right side. So that's the road surface we identified, and then we will be monitoring this particular area for vehicles. You may also know you want to apply for AI, except some approach that's not supervised. Most of the methods are still supervised learning. We collect the data from our Washington State cameras. In the Star Lab, we have the 2 fibers connecting to the Washington State DOT's traffic monitoring system. There are about 1,500 cameras, so we can access the live signal and collecting data. Like these are the locations that we use the camera to download the pictures. For example, these example pictures, as you can see, we have wet pavement, dry pavement, snow covered, or like icy pavement, etc. And we use these pictures, try to train our model. And after we train our model, we can do the kind of analysis and compare to see how well the models has been performing, right? So we see like there are different categories of road surface condition, like a dry, snowy, partial snowy, and rainy, right? So this, we can see like the dry pavement situation detection is accurate in 97.5%, and the rainy condition is 85%. The rainy condition is often confused with the partial snowy, like 5.4%, and the dry condition and the rainy condition, like the mist classification, 7.6%. So this is still pretty good considering the definition, for like what is defined as a partial snowy. You have to have a human decision, hey, okay, when this is going to this many percent, you consider this is, partial snowy. And that's normally judged by human eyes, right? When you label the picture. And certainly when you use video camera to monitor a particular section of road, depending on the distance from the camera, right? The further away it looks smaller, right? So that kind of judgment has a lot of challenge. So that result is considered a pretty good result. As mentioned earlier, we also need to be identifying the blob, like the moving blob, and then try to use the deep neural network approach, try to identify, is this a truck or this is a car? You see like this box, this blob, we use the deep neural network, identifying this as a truck, and here there's some cars. So after you do this kind of analysis, the data we collected in Washington may not be working perfectly when the sensors deployed in Norway. So we have to do transfer learning. We also use the mobile net, pretend on the image net, and fine-tuned using the mile vision, traffic camera data. So this is actually after we do the kind of transfer learning. So you can see the accuracy for vehicle detection, like a car, truck, bus, bicycle, and just background, right? So the background detection, we get 100%. With different kind of vehicles, we can see car is 91% properly identified. For bus, this is 96%, and cyclists, 95%, trucks, 87%. Because truck is long, sometimes people get confused with car or like a bus, right? So there are some misdetections between bus and other categories. But still, in general, I think this is still a very good approach. We have been using the classical method to do the same thing. The result is not comparable to this AI-empowered methods. Anyway, I know like we have to leave some time for question and answers, so I will just stop introducing, the example applications of AI in transportation engineering. But as a conclusion, I just want to assure everyone that artificial intelligence is a very hot area with a lot of potentials. It is particularly promising today because of the improvement of the computing technology and also the increasing amount of data. Maybe you also heard yesterday, actually the Congress passed the infrastructure bill. So we'll have $1 trillion level, investment in our infrastructure. So this will be, ending up spending for like improving our infrastructure system. And the newer infrastructure system is going to be AI empowered. So there will be a lot of future opportunities. I showed you just several examples. We have a lot of other work going on. But I think you can get a sense from what I just presented today. At the same time, transportation area is just a new emerging area for the technology investments. You can imagine automated vehicle, right? So that's in the transportation area. Mobility as a service. Maybe you consider in the future when you travel, you don't need to have your own car. You just like use the service, right, offered by the service providers. And this is going to be easier and more effective after automated vehicles are deployed. There are also other things like how about we use unmanned aerial vehicle to investigate what's going on with our infrastructure. For example, maybe some cracks on the bridge people cannot go up in the sea, but you could fly a UAV, go there using the video sensing, try to identify, is this infrastructure that we need a serious repair, or that's still okay to keep operating, right? So there are just a lot of these opportunities. And I think your knowledge you will build through the FTC will really set a very solid foundation in transportation. So anyway, I just want to encourage everyone, investing your time in the FTC and also investing your time, look at our practical challenges, how your technology and your knowledge, your skills could be used to address these challenges. I think transportation is a great area that everybody would have room to use your technology, use your talents. So we will come to you if you want to study transportation, and particularly if you want to join the University of Washington. You can certainly email me for any questions you may have, or you can bring the questions up online. Julia, I think my presentation is done. Maybe I'll be happy to answer questions.
Okay, great. So we actually have a question right now. Someone asked, are there any privacy concerns with using monitoring for users?
There are certainly privacy concerns with a lot of the monitoring purposes. That's why we're actually hiding the privacy information. For example, if you use video to track pedestrians or vehicle, and that certainly have a lot of privacy concern. The technology we're developing, for example, the one I presented is the mass sensor. So the work is done in the sensor. So for example, there's a vehicle and we detected this vehicle at this location. In another location, this vehicle showed up again. So we do not track the license plate. It's like you detect the vehicle, keep the vehicle feature. Let's say this vehicle is a Honda Accord, silver color, and in the downstream, you also found the same kind of vehicle. And using the feature matrix, you can judge, is this the same vehicle, right? So that way, the privacy information is contained in the sensor, in the edge side, will not be really transferred to other places. There's always a balance. There has to be a trade-off between the privacy and the information needed. Everybody know you are uploading your personal information when you're using Google Map. But why people are still using that? Because the service is super valuable, right? You want to get your own travel time information, your route selection information, and that's really valuable for you. So you are willing to contribute your own information, try to help the service. So that's a great question. And certainly privacy protection is a very important thing in transportation research and applications. And that's considered.
All right. Yeah, that makes a lot of sense. Thanks. We have another question. It says, you previously mentioned that Stanford said AI in traffic systems was something that people would just have to trust. What do you think needs to happen until people feel comfortable to do that?
I think if you guys look at automated vehicles safety record, automated vehicle is obviously safer than the average driver, right? So let's consider if you want to use automated vehicle, you would have to trust the AI, right? Because automated vehicle is directly using the AI for identifying the moving objects surrounding the vehicle, making decisions, etc. So I think that's a kind of natural process. It may not be one day everybody would trust a particular thing. There's always, some people would trust it. Just like Tesla started, very few people were using this EV. Now Tesla, you have to wait to get a Tesla, even you want to buy, right? So I think that's a natural process. And people actually have been trusting AI. You can see there are a lot of, you make phone call, actually may not be a person talking to you, it's a robot talking to you based on the artificial intelligence. In my office, I actually have a Alexa device from Amazon. So I just ask, hey, Alexa, what's the temperature? So what's the traffic? It tells me those things. I feel it's very beneficial. I don't have to spend my time, seeking online. And when I feel tired, I can also say, hey, Alexa, play music, and it will just do that for me. I feel that's pretty cool. And if I'm trusting those things, I guess there will be people similar to me also trusting AI naturally, step by step.
All right, great. And the next question is, what kinds of people do you think would succeed in the transportation field? What kinds of jobs are most needed right now?
That's a great question. Actually, my background, my first degree was structural engineering. And I have my second degree in construction management, the third degree in transportation. After I studied transportation, I was super interested in intelligent transportation systems, and therefore I also got a master's degree in computer science. Transportation is a very big domain. Maybe you heard about transportation planning, transportation operations and control, logistics, supply chain, freight transportation, transportation policy. So basically, I feel transportation is such big domain, everybody could find their comfortable zone. But what is mostly needed, I would say, is in the emerging technology area. Most of the existing transportation professionals have been trained through the classical civil engineering system. They understand how the roadway is designed, how the bridge is designed, how to operate those things. But very few of them actually have ever learned about data management, how to use database, how to operate a traffic sensor, how do you do like data mining and big data analytics. So if you're a data scientist interested in transportation, I'm sure you can get a very, very good job because there's plenty of jobs there. You see like Uber, right? Uber is going to kind of bring in a lot of new ideas, new way of operating, the service for like travel. So it beat the classical taxi company badly. There's also newer companies doing something similar to Uber, like a Convoy doing the kind of freight transportation using the Uber concept. So there's just plenty of new things coming into the transportation field, and that also opens up a lot of opportunities. Just like our students previously mainly work in the classical area, in the recent years, I would say majority of them is working in the new mobility companies. So that's the trend, and that will continue to be the trend in the years to come.
All right, great. And I actually have a question of my own, which is what is the difference between traditional transportation jobs and the new mobility transportation jobs?
That's a good question, Julia. So the classical jobs are more or less in the side of like infrastructure design, construction, maintenance, and the management. For example, you do like highway construction, highway design, highway traffic signal control operations. The new mobility job is, for example, there's like a Uber bike, right? Uber bike, the scooters, when they come to the city, how do you manage these things? And how do you encourage those kind of service to be serving people who need the first and last mile? How do you want people to reduce their single occupancy vehicle driving? You could get more people, using the same car, try to reduce the number of vehicles on the road. At the same time, you can reduce the emission. And how do you open up new opportunities? Let's say the Uber kind of service, right? That's a typical new transportation kind of job. And you may also know Apple company is trying to develop their automated vehicle, and how the automated vehicle perform nicely on the road. A lot of these automated vehicle control algorithms are designed by computer scientists or automotive engineers. So that's why if you look at the automated vehicle crashes, they get more crashes like other vehicle hitting them. It's not because they actually crashed into other vehicles. This is typically because their behavior is not expected by the human driver. So this kind of work, how do we make these robots to be interacting with human as expected and comfortably? So that's also the kind of new mobility job.
Okay, great. Well, if you, Professor Wang, has anything else to add and there's no more questions, I think we could just end this event right here. All right, thank you everybody for coming, and thank you, Professor Wang, for presenting AI applications in transportation engineering.
Thank you,
All right,
Julia.
thank
Thank
you.
you, everyone, for listening.
All right, bye.